Bienvenidos nuevamente a este primer encuentro internacional Red Abisure, Alianza para la Investigación de la Biomasa y la Sostenibilidad. Para quienes nos acompañan por primera vez el día de hoy y nos acompañan también a través de la transmisión, Abisure es una red internacional conformada por organizaciones, científicos y profesionales de los sectores público y privado. Es liderada por la Universidad Nacional de Colombia. Actualmente, las líneas de trabajo de la red son la transformación
of biomass, mathematical modeling, optimization of physical and chemical processes, obtaining high added value products, and sustainability focused on the life cycle analysis and circular economy. We opened this talk with the perspective of the future of biomass in Europe and Spain. And we have a speaker from Spain, from the University of Zaragoza, member of the Club of Rome International, and creator of the CIRCE Foundation, the Center for Research of Energy Resources, a professor at the University of Beijing. But he asked me that when he introduced me to do it with my most important position, which is being a student. Welcome, Professor. Thank you. It is my pleasure. I'm going to take my mask off because it'll be tough to speak otherwise. Thank you, Farid. It's my pleasure to be here, and this is my second home. Thank you. But I would also like to have an international passport, because all of us live in one planet and we're destroying that planet. Very well then. My talk is gonna be twofold. First, because of Farid, who asked me to talk about the perspective and the situation of the biomass in Europe, and then talk about what you do, he said. And you could say a lot of things about what you do, but I don't like to talk about the degrees I have. I prefer to focus on providing messages. So the first part I'm going to focus on is going to be how I see and how I'm going to be based on talks I've had with different people from Spain and Europe in regard to the future of biomass. And I'm not going to be able to cover everything, so you'll see what I'll focus on throughout my presentation. So I'm going to talk about this topic. And the thing is that biomass is being used by everyone and for everything. So the thing is, how much of that biomass are we using? And some colleagues from Finland did a work called Biomass Use in the European Union in a net zero economy. And this, well, I've used their message. I'm going to be brief, but this is important. Let me see if this works. You can see it, but not very well. What has happened in the past 20 years in Europe, and what has happened is that demand for biomass has grown by 150% in 50 years. If we stay on this path, how much are we going to use it? And what has that biomass focused on? Mainly on heating. It's like as if we had a cathedral and we needed bricks, and we pretty much brought down the cathedral to build homes. And energy production, electric production has multiplied by a factor of 5. So talking about carbons, but the thing is, we are in a situation where there's enormous growth, because it doesn't make sense for us to stay on the path we've been. If we look, but before I say anything, I'll say that that growth is in hexajoules. It's a unit that is not widely spread, but I switched it to another one which is easier to understand, which is terabytes per hour, or hour terabytes, which is the biggest center in Colombia, the thermoelectric station, the most powerful one. Which is it? 150? I think that's small. 400? Okay, let's suppose it was a station with 400 megawatts, just to state a number. And usually a thermal station can have 7,000 hours of activity, right? Per year. Out of 8,800, that's 7,000. So 1 hexajoule would be equivalent to 80 power stations. And the number of hexajoules used in Europe is 6. So 6 times 8 is 48. 480 stations, as big as your biggest one in Colombia, working 7,000 hours. This is the energy being used in Europe. Very well. Let's continue with this hexajoule number. So, out of those, let's see what happens. It turns out that, yes, this is the part relating to the wood we get. And from that, we extract something I haven't discussed. Let me go back. Where am I going? I don't even know where I am at this point, but don't worry. I'll find it. Here we are. Okay, so there's a set of roots that stay, also leaves, branches, and so on, industrial products. Waste, agriculture per se, and of course paper, wood waste, etc. Once again, we're talking about 10.2 hexajoules. So the most important thing is the part up here, which is relating to direct wood. This is the agricultural part, and this is the recycling. But the thing is, everything that we're seeing here is waste, and at some point it will be. In other words, there's enormous potential for the use of waste. And if we look once again, why, the purpose, you can use it for a lot of things. Products such as paper, of course, furniture, fabrics, chemicals, and new materials. So, pretty much everything is linked to those big numbers. So we have to think that this is what provides the most added value. So, biomass. What do we have to do? So, the message that has been gathered by the European Union is that we got to use biomass in a sustainable way. It's evident because it's scarce and it's valuable. And the demand for wood is growing at a pace that is just not going hand in hand with supply. So this means we're going to have to import. And we're importing so much biomass, not even knowing its ecological path. We receive it, but we forget about the ecological print. So we got to focus on the most valuable applications of biomass, not anything, not just anything, the most valuable. Because we cannot use biomass to heat up things. So we gotta rely on the idea that bioenergy for big consumption doesn't make sense in the future. But there's much more. And it is that, okay, we gotta focus on that added value, which is the development of biorefineries. Like I said before, or like it's been discussed, you've opened up the path, because the scenarios being discussed today are talking about that it would be required 70 to 150% increase in biomass use compared to our current situation. So that's an increase of 70 to 150%. And my question is, how about the soils? And the biomass footprint that is imported, how about that? In other words, it's not just about adding value to biomass, but also being responsible about the impact of biomass, not only at the local scale, but also thinking about other means and other places. So let's look at a question. We're thinking that biomass is carbon, hydrogen, and oxygen. We were just saying the other day about how we gotta take oxygen away to increase the heat power of biomass. But biomass needs macronutrients, magnesium, calcium, as well as other elements, iron, chloride, and other beneficial elements, sodium, selenium, aluminum, and those are not being provided to biomass. Anytime we cut a tree, a plant, whichever it may be, we are decreasing the mineral content of our soils, and we gotta give it back. We're creating a material footprint that is not only about hydrogen, oxygen, and carbon. So we cannot think about biomass as something that is above the ground, but we gotta think about what's below the ground and from the soils. up, having a vision that looks at the life cycle. So, some first conclusions. The European Union, and I believe the world, needs to prioritize the use of materials and chemical products. Demand is growing so much that we need to avoid producing external footprints. And also, bioenergy, when we burn something, it turns out that we produce ash, and that ash is considered something bothersome, to simplify. But that ash is the footprint that we took from the ground, and now it bothers us. So it cannot be that that's how we act upon things. And the material footprint is ignored. Fortunately, we have groups here, and that's why Farid asked me to talk earlier, but I said, no, I want to hear what others want to say or have to say first, and then I'll talk. And there's a matter at hand here, which is that some are working on biochar, given to feed microorganisms in the ground, and that way they work for us. Very well. Bioenergy must focus on wastes. I do not agree with agro-energetic cultivations or crops, because they don't take into account that material footprint, and they need fertilizers, when in the future the people that are going to need food are going to need at the same time those mineral fertilizers. And the amount of phosphates in the planet is decreased. So the amount of people that can rely on those depend on the availability of them. So that's the first part. The second part is that we need to talk about the policy that is being carried out, let's say, in the short term. But I cannot talk about everything in our limited time. And of course, I gotta talk about those topics that we're working on. So I focused on biogas, and there's a reason, and it is
because at the beginning you haven't given it a lot of importance to biogas, and I think that's okay, because that means that this is a mature technology, and that's important. Very well, now let's focus on that idea. And you will see why I will be focusing on this idea, and why I'm saying that we need to face the future and the problems that come with it. Based on the research conducted by some colleagues and the government of Spain, we were talking about this topic, and we reached an agreement because we wanted to give you a message about biogas. These are some of the publications that I have been working on. We all know about biogas. It is created by the anaerobic processes, and it comes from different waste. We need to make a distinction between biogas and methane. So here you see that between 25 and 45% is CO2, and that cannot be injected directly in a gas pipe. We need to remove the water, of course, the nitrogen, the ammonia, hydrogen, sulfur. So we call this biomethane because it has a biological origin. And this is very well known. The thing is where it comes from. These are things that we all know. We need to see that we can obtain it out of agricultural waste, from industries that work with food, from wastewater treatment plants, the one that comes from solid organic waste, urban waste, and obviously from landfills. Here in Colombia, you have landfills, and we have all these things. I see that you are not working enough on this. And I insist, technology is more mature. However, it requires a PRL of 7, 8, 9, but we have to do this. So when we digest this, something very important comes up. It's not a waste. This is something that we call digestato, and this could be used as a fertilizer. So we can return that digestive component to the soil. It is not a waste, it is like food for the soil. So you know what this is about, and let me continue. So what's happening in these 5 or 6 sources of biogas? We are sending them over. We are sending these sources overseas because digestion happens in a natural manner. It is anaerobic, and that methane has 28 times more impact than CO2. So we're making a favor to the nature if we use the waste that comes out of those sources and we convert it into CO2. I'm sorry, if we convert this into biogas, and that biogas in turn is converted into CO2. So we have reduced the weather climate impact, and we are using that digestate to make fertilizers. If you tell me that it's a mature technology, I don't think so. Let me tell you that this is a technology that is necessary, and we need to work on it, and we need to develop it. And there's more. Resources become more valuable. It is a renewable energy, and it helps in the development of rural areas, because we want to hide these things and we want to keep these things out of the city. So here we have the GHG production in Europe, and we have an 18% of emissions. I don't know what's your position in terms of animal production, but in our case, I'm from Zaragoza. Our province is Aragon, or our region. And we have 1.5 inhabitants, and we have around 8 million pigs. And they are producing several issues in all the soils due to the urine and all the waste, and that needs to be converted into biogas. And on the other hand, larger emissions rely on transportation and industry. So we need to reduce those emissions, and we also need to recover, we need to reduce these emissions in any type of residue and also in the agricultural processes. So if we reduce emissions in the agricultural part, this will become a solution that will reduce industrial and transportation emissions. So it's a win-win situation. So we're talking about biogas, but biomethane is even better because it can be injected directly into the networks or the gas pipes. So it doesn't require any new infrastructure. So following this train of thought, we wonder what happens in Europe, or what's the overview in Europe. Let's check the gas infrastructure in Europe. This is Russia. This is the Nord Stream. This is what comes from Ukraine. From the Ukraine, it goes to Germany, part of France, because Spain and Italy, in Spain and Italy, we're using the GNL that comes from Argelia. So there's no connection from this provider to the center of Europe, but let's say that Europe depends almost 100% on Russia. Well, the thing is that before February 24th, there were some plans, and we still have them, regarding the situation about what Europe needs to do. So by 2050, we need to achieve zero emissions. And this is why a lot of money is being invested on the circular economy, renewable energies. So we need to decarbonize the economy, and that decarbonization needs to be achieved by creating new jobs and being competitive. Therefore, we need to develop technologies. We also need to emphasize on the circular economy. These are some of the messages sent by the European Union. This is before the 24th of February. After the 24th of February, a new problem emerges, and it is called Russia. This problem changes ideas. So what had been formulated for years 2030 and 2050 is being formulated for yesterday, not for tomorrow. And we have to do everything that is within our reach. So renewable hydrogen, we need to import biomethane and renewable hydrogen. And gas imports from Russia. Today, we saw that there are some issues in Germany with the use of gas in the industry and also for heating purposes. And it affects us a lot because you know that we store that gas. But when the winter comes, we will have spent all the storages and we will be demanding more than what we have. Very well, so a new project is created. It is called RE-Power EU, aiming at reducing at least 155 billion cubic meter of fossil fuels in the EU. So there has to be a great effort needs to be conducted to boost biomethane production to 35 billion cubic meters. So we need to remember that replacing is not just a matter of replacing. We also need to stop using certain things, and we need to reduce that number. It can be done by replacing or by reducing. And the European Commission estimates a very significant development of biogas. By 2050, biogas could account for 20 or 60% of the current demand for natural gas, between 20 and 60%. Now let me go back to what we've been talking about in terms of biomass. And remember that we were saying that 40, 80 power stations or thermal power stations, such as the largest one here in Colombia. With biogas, we will be talking between 20 and 60% of the current demand for natural gas. This is huge. Huge. In Europe, you may have seen that the gas networks are highly developed. The gas is very clean. I don't need to call anyone to bring me a container of gas. I don't need additional space to store it in my place. It is efficient. It produces the heat that I need, and companies are saying gas is wonderful because it gives me heat and energy. So those companies or the residential sector that use it for heating purposes and for cooking purposes, this has extended, or it has spread very quickly. But what do we do now? So my message is between 20 and 60% of the current demand of natural gas should be replaced by biogas or biomethane. Evidently, that solution is not just provided by biogas or biomethane. We also need other applications such as heat pumps to produce thermal energy. This is also an opportunity, and also hydrogen. Thermodynamics tells us that converting renewable energy into hydrogen and then take it to a network for distribution, it's less than 20% of the electrical energy produced by a photovoltaic station. It depends on the technology. In other words, competition between hydrogen, biogas, and biomethane. Now the question is it possible to make a change? And the answer is, yes, we can make a change. Yes, change is possible, but we do need that all of you who are working on this take it very seriously. Very well, there's an idea. 350 municipalities in the European Union are already using the waste the waste that come from biogas sources, and they're producing it. Can you imagine that a city in the Mediterranean, we are not as cold as people who live in the northern areas? So can you imagine producing their own biomethane for heating purposes and for trucks and buses? It can be done. Okay, before February 24th, biomethane production in Europe went from it had a growth of 25% between 2019 and 2020. Additionally, if we talk about the biomethane and biogas production in Europe with the current techniques, we will be able to produce 191 terawatts per hour. So it is possible. What has been happening in Spain? And why do I talk about Spain? Because in many aspects, we are closer to the Latin American situation than to the European situation in general. It is important to boost biogas production, but what has happened? Spain is almost at the bottom of the list in terms of biogas production and waste management. Biogas hasn't been used. We've conducted some studies, projects, but people say it's very expensive, or let's say, what do I do with the gas if I cannot transport it, if I cannot convert it into biomethane, if there is no network? Who is going to help me? There are so many things that prevent technologies from developing. And it turns out that Spain is the largest fine in a European country has been due to the lack of development in Spain, because we haven't produced enough biogas, and 18% of GHG emissions in Spain come from agriculture and waste. And these are two sectors that could be perfectly developed, because we would be reducing that 18%, and we would be producing, and we would be working towards the environment. Currently, we have over 8,000 gigawatts per hour, which is only 10% in gas consumption.
Y de biometano, pues 95 gigavatios hora. Me parece que hay solo 6 en estos momentos.
210 active biogas plants in Spain. And Sweden and Denmark are replacing 20% of their gas consumption, 20%. And they're doing this with biogas. So it is necessary to develop this because other countries are already doing it. So this is a map of the situation of gas pipelines in Europe. So there is no connection with Europe. And but we do have plans that can bring by boat this, therefore we can bring gas from the US And unfortunately, since there's no connection, we cannot help much France and Germany, so it becomes an issue. And having a good infrastructure, a good gas infrastructure is good. Unfortunately, we are not connected. It is said that Spain is almost an island. So what's the potential? What's the Spanish potential? The government, I think last week, a few days ago, changed the situation. Well, now let's think about rethinking this situation. Now they're talking about 10.4 terawatts hour per year. This would avoid the emission around 2.1 MTCO2. And they have their own calculations, and now they're saying that this has to be multiplied by 3. And evidently, CO2 emissions would be reduced, and also the reduction of emissions by 2020 would be very big. But some people think that if we could have agro-energy crops, maybe we could reach 137, which would be 10 times more than what the government said. We as researchers need to analyze all the possibilities of everything. And we need to be working hand in hand with companies. We cannot work in an isolated manner.
We cannot have all our efforts on basic research when the country needs it urgently, because this is generating inflation close to 9%, which is incredible, because we've had inflations that are 0%. We gotta change that. Okay, so what are we talking about? 34 terabytes per hour is 20 power plants of 0.5 terawatts, 40 of 0.5 terawatts is this 137. And in Europe, it is said that you can get 120, but for 2050, for the year 2050. So there's definitely potential. But, Professor Manuel, we're talking about a need for regulation. We have to regulate. Even though electrical energy is well organized, thermal gas energy is not well organized. We don't have a structure as well designed to favor this type of production. So we need a system of source guarantees or guarantees of origin, because if I'm getting natural gas, I'm not going to get it from Russia or from some country that is not doing it the right way. And we also need a set of ideas which are regulating instruments, sectoral instruments, economic instruments, cross-cutting instruments, and of course the promotion of research and development and innovation. I'm not going to go into detail, but I do want to say that we're not talking here with politicians or economists. We're discussing this amongst technicians, so we got to have a talk about it. So what have we learned, or what should we learn from this? In my opinion, there's there's something to take into account. I developed a research center where there's 200 people working right now. We created this center at university, and we've been working hand in hand with the industry. And it's only hard to work with the industry in the beginning, because if we get results, the industry says this is wonderful, it's cheap, and moreover, it allows me to be ahead of the competition. So to me, working with companies is flexible and normal. You gain a lot of results, and now more than ever. What are we going to do with gas? Well, look, first of all, we've seen gas helps in the fight against climate change. It lowers emissions, and in many cases, these emissions are not counted because these emissions are so hard to quantify. Those are lost emissions, if you will. It gives us power autonomy. We have circular autonomy because it's not just about getting
el residuo
the
y
waste and use
utilizarlo,
it
producir gas, sino el
back into
digestato,
gas.
utilizarlo para los suelos. Hay una cosa que creo que nos pasa a todos los países que de alguna manera tienen una agricultura más o menos desarrollada, y es que las zonas rurales tienen desde luego menos desarrollo que las zonas urbanas, y el resultado es que necesitan ingresos, tecnología para desarrollarse. Entonces, la política agrícola puede ayudar, cuando se desarrolla el biogás, a que se desarrollen también las zonas rurales. Y luego, pues eso, se mejora la competitividad de las áreas rurales, y luego se necesita un desarrollo tecnológico de I+D+I. Bien, pues al final el mensaje es que el uso del biogás es una solución esencial en la gestión del uso de los residuos. El biogás y el metano debe ser considerado como fundamental y complementario al vector de energía eléctrica. Tendrían que tener el mismo tratamiento, digamos, regulatorio. Y evidentemente hay demasiadas pocas plantas, y eso está ocasionando, curiosamente, que España tiene que pagar multas por no tener demasiadas plantas de tratamiento de aguas residuales. Bien, pues esta es la primera parte de mi charla. Es el tema de que creo, porque podía haber hablado también de los biocarburantes y también de la biomasa, porque también he estado hablando con otras colegas de las distintas, y de hecho, no sé si lo habéis puesto, no lo he visto en el pendrive que habéis dado, me extendí más allí y menos en el tema del biogás, pero a mí me parecía importante hacer este esfuerzo porque creo que vale la pena que desarrollemos ese tema. Bien, pues ahora parto a una segunda idea, y es completamente distinta. Ahora voy a hablar de lo que estoy haciendo con mis equipos desde hace más de 20 años, y es una palabra que espero que os acordéis: pristinia. Vamos a ver de qué vamos a hablar. Y es responder a la pregunta de una manera más profunda acerca de qué pasa con los suelos. Y qué pasa con los suelos significa algo. Y voy a ver qué ocurre cuando estamos
And it is
trabajando
answering this question in a deeper way. What about the soils? And that this question has certain connotations. So I'm going to see what happens when we pose how to measure the degradation of the grounds in the planet. Brief but important messages. 1/3 of fertile lands in the planet are degraded strongly. And it's destroying around 24 million tons per year in excess of supply. In my opinion, fertile soil is the biggest John Doe in terms of natural resources. And on the other hand, it is possibly the most important out of all natural resources. Because if we don't have the soil, we don't have food. And if we don't have food, the planet is not going to be able to sustain its living in a situation where we don't have fertilizers. So for intensive agriculture, it's good. We need ammonia. That's okay. We separate the nitrogen from air. And with the Haber-Bosch synthesis, we turn it into ammonia. And from that, we have ammonia, and that's fertilizer. The footprint of ammonia-based fertilizers is enormous. Some colleagues talk about 3 to 4% of all energy resources in the planet are being dedicated to the production of ammonia. But consumption has gone up tenfold between 1960 and 2013. Awesome that if we use nitrogen, plants are going to grow. But at what cost? How many fossil fuels are we using to that end? And in the case of phosphorus, it's multiplied fourfold. And the amount of irrigation is huge. So 80% of the increase in food supply has happened using irrigation and fertilizers. And of course, this is a global issue. It's an important issue because those dedicated to biomass, for the most part, think about biomass from the soil up. And I insist, micro farms of the grounds, microfarming of the soils is unknown, or very few are aware of those. So in Europe, it's estimated that 1.2 billion euros per year do that. A high percentage of the hectares of land are having a lot of erosion, and that turns into many tons of 5 million tons of production. Why is this happening? This degradation, and how much? We're talking about money here, but if we don't know exactly how to remedy this situation, how much each remedy costs, and how to have a diagnosis of the soil degradation that is more accurate than just the amount of euros that are being used to that end. That's not an indicator. I'm into thermodynamics, so I have to explain an idea. I suppose some of you are familiar with the concept of exergy, but that concept Well, I remember when I talked with my physicist and chemist colleagues, and if you put that into Google, it's gonna change exergy for energy, but it's an important concept, and it is also very simple. When you talk to an economist, they talk about entropy, and they say that the entropy is increasing in the planet. But okay, how do you turn that into numbers? They don't know how to do it. But exergy is very simple. It's the energy in a system less that part of the entropic situation that cannot be converted to electric energy, for instance. So, for the share of energy you have, you gotta take away the portion that is not workable to produce something like natural gas or electrical energy or whatever it may be. If I have water at 500 degrees Celsius, so there's a lot of potential to produce electrical energy. If I have the same water at 50 degrees, I cannot produce electrical energy even if I have a lot of water. So that concept of energy is useful because every time we do anything, we don't lose energy, we lose exergy. And how much of it do we lose? Precisely the room temperature generated by the exergy that is lost. So if I multiply this by the generated exergy, what I get is a word that we get irreversibility. We can quantify irreversibility based on exergy balance calculations and linking it to entropy. And with this process, no one's bothered, and it is facilitated to ponder about this for everyone. I actually talked about this next topic very recently. I only believe in the second pillar of thermodynamics. I apologize to those that don't agree. And the second principle stated the following. 1 hour ago, you were 1 hour younger. You will never be as young. The date of irreversibility leads to degradation. And thank God we have the sun. But only 0.24% of energy that we get from the sun is gonna stay as biomass in the planet, because the rest is gonna be spread throughout the universe. So it's a good thing biomass does its work, but it has a very low performance. So this idea leads to one proposal, which is that whatever we do, sooner or later, we're going to have a completely degraded planet. And what does that mean? It means that due to human actions, we're going to have burned through all available fossil fuels, and we're going to have an atmosphere full of fossil fuels. 0.7%, which is less than the amount that we get 700 million parts per million. It seems like a lot, but in reality, it's less than the amount of trees in the atmosphere. And that's enough to burn all fossil fuels available in the planet. The poles, the glaciers will have melted. Temperature will have risen, but also the levels of water. And we'll have a water that will be almost completely salty, because salty water does not turn into sweet water if it's not because of the sun. Less than 0.001% of all of the sweet water in the planet is in rivers. There's a lot in the Antarctic and mainly in Greenland. But based on extracting all fossil fuels that are referred to as mineral deposits and fossil resources, we're not going to have to extract anymore. We're going to have stones on the streets. 0.01% of all of the planet's surface is minerals. So for that degraded or degraded planet, we call thanatos, which is the same as death. And what does the energy analysis need? It needs a reference level, and based on that, everything that is on top will have exergy. If I have this and I drop it, it'll fall on the ground, and that ground will be my level of reference, so it'll be about 1 meter. But if I drop it on the street, the distance will be a lot greater, so the capacity to produce work of this depends on the level of reference we have. So we went to the worst case scenario, and the worst case scenario is thanatos. And we said, okay, any natural resource has more exergy than that which has nothing. And we posed, okay, the following. Let's analyze the atmosphere. Let's analyze the hydrosphere, the lithosphere, but why not to study the soils, the fertile soils? So we posed that question, how to assess exergy of fertile soils, but not fertile soils that are not so fertile that they're amazing, the degradation of fertile soils. Okay, so these are 2 books. One of them was written by my daughter and myself in 2014 for the Imperial College of London.
And this one was issued or published last year by Springer. And even though both talk about Tanacia, we are saying that the natural footprint of renewable energies, solar energy, wind energy, photovoltaic energy, they all have a material footprint, and it is being ignored because now we're going to move to renewable energies, but there's lithium. We're going to move to electric vehicles, but there is tantalus. A vehicle, an electric vehicle, has 55 chemical elements, different chemical elements. And what is the footprint of a mobile phone? Over 35 chemical elements you are holding in your hands. So the material footprint is in the oblivion. And there's going to be a problem with renewable energies and digitalization. And I wonder, what is the footprint of digitalization? We conducted a study about the information storage centers or hubs, and we need to talk about the energy footprint and the material footprint. But let's cut to the chase. And the first message, this planet is being converted into a planet that is in decay, and it's just a matter of time. But if you take a look at the planet, we have the atmosphere, we have the cortex, the upper cortex, we have the core, but it is very curious that fertile soils in average don't have over 15 centimeters. Evidently, here in Colombia, it is 2 meters. But unfortunately, the world is not Colombia. But yesterday, when we were going to have dinner, when we were going towards the airport, you wonder, this is what we need in this planet. Unfortunately, this planet has more arid areas than the areas that we have here in Medellin. So the thing is that we have the atmosphere, the lithosphere, and the fourth dimension, fertile soils. So we need to know what to do with the energy analysis of these fertile soils. First, soils are very complicated. Those of you who have worked on this know more than I know, because there are so much information about it, and it is very complex. It is fascinating as well. It is incredible. Okay, first, it has a physical structure. The texture, it varies. This texture varies. Usually, it has limes, gypsum, and clay in different compositions. And we cannot say that the texture is constant, but it also has some biological aspects. It also has some biological aspects, and that macro and microfauna do good or bad. But we need to know what we have there. The human being found out that there were some birds that could be domesticated, the hens, and some wild boars that became pigs, and some bulls that became cows, and dogs, or wolves that became dogs. So we learned how to domesticate those animals. And there are fungi. And in addition to that, there is dead organic material. So we have one part, that dead chemical matter, whether it be organic or inorganic. So we need to have a diagnosis. So the life of a soil is more complicated than diagnosing through blood work your health. So the complexity is incredible. So let me go back to what we were talking about before. Nutrients, plants' nutrients. We have macronutrients, we have micronutrients, we have iron, nickel, copper, and they are all necessary for plants to grow. So We need to do it because we have enzymes, lipids, transfers. I love it when we see these trees that you have here. And so what is the pump that is used to move the magnesium that is on the soil or the floor, goes up to every single leaf? What are the forces in nature that take whatever is on the ground to the leaf? And we don't realize the complexity of all this and the energy balance and how nature does these things. Very well. Additionally, we also come across something else. This is the soil, and I always do this. I have this, I have the same soil, but with fertile soils, things are different because there are some things that are bad in excess. And if we have a deficit of those things, it is also bad. There are others that are always bad, and there are some that have a limit in terms of optimization. Unfortunately, we have the Levy law, which is the law of the minimum. So if I don't have phosphorus, but I have everything else, I won't be able to produce anything because the barrel will break through that hole. So there is a complexity that we need to address. What's the optimal point? And everything that goes over that or falls below that is not useful. However, there are some things that can be assessed. But it turns out that those toxic elements, we have cadmium, we have vanadium, and they have toxic compositions, and plants cannot overcome those conditions. Plus, it depends on the type of plant we are talking about. And the same thing happens with other elements, nitrogen, sulfur, phosphorus, magnesium, calcium. They also have a minimal composition, toxic composition, and a maximum composition. In other words, this is more complicated than what we were doing with the hydrosphere, the atmosphere, and the cortex. And the thing is that we wonder, are there any optimal soils? What is an optimal soil? Maybe you have it so close here that you don't even realize it. The thing is that our colleagues have studied an optimal soil and all the elements. So what we get is a situation. Let's say that this is an optimum soil and this is Tanatia. So what are the soils in the planet? They're not even in the optimum soil part, neither on this other part. There's a space here in between, and we are here. Some are below, some are above. We are around this space. So the thing is, what is an optimum soil? Yes, biomass doesn't have to go from the bottom up, and I consider myself part of the team, and I'm not working on biomass to the top. Some other people are. May I continue?
Vamos a ir un poco más
Okay, let's go a little bit faster. We were talking about the optimal soil. It is called Pristinia.
¿Qué es pristina?
What does Pristinia mean?
Pues mirar, pristina, pristina,
Or
¿qué es pristina?
pristine. It comes from pristine,
Impoluto.
something that is not polluted, something that is very clear. So that soil does not exist. And Tanatia doesn't exist either, fortunately.
Tenemos que hacer lo posible para nunca llegar a Tanatia.
So let's hope we never achieve Tanatia, but we may have,
Impoluto.
or is it possible to have pristine soil?
Este
The question is
pristinia
that Pristinia, this planet, is not as simple as Tanatia
porque la textura,
because
la textura
the texture of fertile soils across the planet vary. So Pristinia is not the same here in Medellin as it may be in Europe or in the Sahara Desert.
cada suelo tiene
Every soil has its own texture, and every soil has an optimal soil. Therefore, it is more complicated than that.
y la idea
And the idea is to see, and you can see it here,
entre Tanatia
between Pristinia and Tanatia,
podemos estar por algún sitio.
we may be around this area, but now there's no number. Now we're talking about a number for texture,
Poco en nutrientes inorgánicos,
nu-
nutrientes
organic nutrients, inorganic nutrients,
microorganismos.
and microorganisms.
Es decir,
In other words, it is necessary to analyze from an exergy point of view what's happening with all the components of the soil.
esto es lo que hicimos.
And this is what we did.
Es que esa análisis
That exergy
teníamos
analysis,
que plantear la huella de
first we needed to know
una cosecha
we needed to start with a crop.
acostumbrada. En fin, bueno, y entonces tenemos allí primero
Here we have some mechanical processes, fertilizers, pesticides, water, diffuse emissions, and then
a los suelos,
the soil part, erosion, nutrients that are lacking,
orgánica que falta,
biochar,
salinidad,
salinity,
etcétera.
acidity.
Estudiar todos esos.
So we need to study all those effects.
Entonces,
Very well, now
las propiedades
physical properties
las podemos
can be assessed
con exergía,
with X-energy
Tanatia, sin problemas. Me da lo mismo.
because we're talking about minerals.
Las químicas que pueden ser
And as for chemistry, inorganic or organic, very easy as well.
no me generan ningún problema.
This doesn't create a problem.
Y además lo puedo hacer para todo
And I can do this for all the elements and the necessary components.
¿Y qué pasa con
What happens with microorganisms?
bien? Pues la idea es que en la materia orgánica, microorganismos,
So the idea is for organic matter and microorganisms
lo que hacemos es lo siguiente.
to do the following.
Es una cosa muy curiosa.
This is very curious. Let's say the dead donkey has the same X energy than a living donkey. So what's the difference between the donkey that is dead and the donkey that is alive? There's only one. It has an organized structure. It is a machine that is in operation. And that machine that is in operation is very complex. And the word complexity is related to information and also to the entropy of information. Therefore, it is not problematic. So, in addition to having an inorganic and an organic component, our bones are calcium 3-phosphate, which is a mineral, just to make it simple. And we have an organization and we have information. So my colleague Jorgensen said that if the dead donkey is a detritus, so the X energy is what I can see when we burn or incinerate that dead element, and that has a value. The chemical X energy of that detritus is around 19.4 kilojoules per gram. So the more complex the system, the more we separate in terms of information with respect to that detritus. A microorganism, bacteria, and viruses have a very small complexity. Other living systems are more complex, and the complexity can be 18 million times more than viruses. And this was studied by Jorgensen, who passed away a few years ago.
So the thing is, we can look at the exergy of the texture, the exergy in regards to Tanatia, the exergy of dead organic matter, as well as inorganic matter that is dead, as well as dead alive matter, which is called exergy. So the result simply, and this work was carried out by Jorgensen, is to multiply by a beta element, which is energy information, with the exergy that we have with the dead donkey, if you will. So here we have that the exoexergy is the detritus exergy multiplied by some beta coefficients that depend on the organizational structure. The beta from Jorgensen is at 61 for fungi. We have the number for bacteria, viruses 1.01, etc. So you multiply this value that is related to the organization, and the final result is that you can have an eco-exergetic analysis of the alive matter or live matter. So it's a DNA topic. So outcomes. I'm approaching the end of my talk here. You can see that in Spain, 1 hectare costs us about 3,000 euros per hectare. That's about $3,000, 3 to 5,000 approximately. If we were to measure the ecoexergy of the ground, which in the end is measured in kilowatt hours, and we paid for those kilowatt hours at the price that we're paying electrical energy today, we would get that that hectare would cost around 2 to 3 times more than what we're paying. In other words, when we sell a hectare, when we sell a territory, we do because we say, well, if I build a house here, I'm going to get more benefit. Or if it's further or farther and it has a different value, I'll sell it for a smaller price. But in terms of live matter on the ground, there's a lot. So we got to value those. But all cities are growing everywhere, saying this is a rich soil, we'll turn it into urban soil, and we'll give it added value. We are degrading the value of soils. So let's look at this, which is amazing. This is the optimum soil in terms of texture. This is regarding nutrients. This is organic, death organic matter, and this is precisely due to microorganisms. I insist, we have microfarms in the grounds, and there are elements, there are animals, there are live beings, and we know this because when we work and put a bottle without a cap in the ground, we see that the soils breathe, and if the soil breathes, it's because there's live beings in there, and you can measure those beings in terms of quantities. So we realized that the organic part is the most important one, and it's the least recognized. So let's not think about it as chemists, let's think about it as biologists, also as chemists and biochemists, but biologists are fundamental. Well, to arrive at the end here of my talk, because I've gone for too long, exergy can be very useful to evaluate the complex issue of soil fertility. And to that end, we need to have some optimum soils. And to define an optimum soil, we use the difference between Thanatia and Pristina. So it's similar to having a blood test, and they tell me, you know, how my cholesterol is, my triglycerides, uric acid, and so on. It's the same thing here. And for each measure, we measured in terms of kilowatt hours. So we can add those, and by adding those up, we get a conversion from kilowatt hours or kilowatt hours not only to money, but also to the necessary energy to get back the quality of that which was degraded. We know, once we know the optimum soil characteristics, it's the same as what a physician would say. Okay, in order to get to that, when you're not there, you need to do certain things, and this is going to be the cost. But the doctor locates not only the reason, but also there's also a measurement. So we see that what a pristine planet would look like and what a Thanatia planet would look like, which we don't want to have. So I want to say that this is not just a research that we're doing that is curious. It is, we've presented this to the European Union, and it's becoming a standard. So this standard is something that you can find in an organizational committee. We presented this in March, and it's being presented as an international standard. Okay, that's what I wanted to share with you.